Every image you've ever seen of our solar system shows it from above. 8 planets lined up in a neat flat disk, the Sun at the center, everything orbiting in clean ellipses on a single plane. It's a useful diagram, but it raises a question that nobody ever asks. What does it actually look like from the outside? What would a traveler actually see if they left Earth, crossed the outer planets, passed the last known boundary of the solar system, and kept going, far enough to look back at the whole thing? The solar system is not just the planets. It's surrounded by invisible structures, magnetic, gravitational, chemical, that extend far beyond anything in any diagram. And from far enough away, those structures define what we look like to the rest of the universe. Let's make that journey. The first thing we notice as we accelerate outward is how quickly the planets disappear. Neptune, the outermost planet, orbits at about 2.8 billion miles from the Sun, roughly 30 astronomical units or 30 AU. The light that left the Sun takes about 4 hours to reach it. From our accelerating viewpoint, Neptune would shrink to a pale blue dot in a matter of minutes, and then it would be gone. Beyond Neptune, space is not empty. The region from about 30 to 50 AU is occupied by the Kuiper Belt, a wide ring of icy objects, rocky debris, and dwarf planets. Pluto is one of the largest known bodies in this ring, but it has hundreds of thousands of companions larger than 60 miles across. The Kuiper Belt contains more material than the main asteroid belt between Mars and Jupiter, and it stretches across a far wider band of space. Passing through it, we'd see a sparse scattering of icy objects drifting in the dark, not the dense asteroid fields of science fiction. The real Kuiper Belt is vast enough that you could travel through it and never come close to any individual object. The emptiness is the point. Space doesn't begin at Neptune. It just gets progressively emptier the further out you go. And then, past the Kuiper Belt, the Sun's light starts to look different. At 50 AU, sunlight is about 2,500 times fainter than it is at Earth. The Sun is still by far the brightest object in the sky, but it's no longer a blinding disk. It's a fierce, brilliant point. You could look at it. The planets are gone. The disk is invisible. What you see is a single star and the dark. Past the Kuiper Belt, something significant happens, not visually but physically. The Sun continuously releases a stream of charged particles called the solar wind. These particles, mostly protons and electrons, travel outward at speeds of hundreds of miles per second, filling the entire space within the solar system. As we travel outward, we've been inside this stream the whole time, but at a certain distance, the solar wind loses the fight. The interstellar medium, the thin gas and dust that fills the space between stars, pushes back. The point where the solar wind finally slows and eventually stalls is called the heliopause. And the entire region inside the heliopause, the zone dominated by our Sun's wind, is called the heliosphere. From the outside, the heliosphere looks nothing like a sphere. The solar system is moving through the galaxy at roughly 43,000 miles per hour, and that motion distorts the bubble. The solar wind piles up on the leading side, compressed into a blunt bow shape, while the trailing side stretches out into a long tail that may extend for hundreds of AU behind us. Astronomers call this structure the heliotail. A ship carving through water pushes a wave ahead of it and leaves a wake behind. The heliosphere is the solar system doing the same thing, on a scale that dwarfs the planetary orbits entirely. At the leading edge, where the solar wind first meets the interstellar medium head-on, the collision creates a region called the bow shock, a zone of turbulence where interstellar particles are slowed and heated. This is the first physical boundary a traveler would cross when entering our solar system from the direction we're moving. Not a visible wall, but a detectable change in particle density and magnetic field orientation, like crossing a threshold that exists only in physics, not in light. The heliopause sits at roughly 120 AU from the Sun, about 4 times the distance to Neptune. We know this distance with some precision because 2 spacecraft have actually crossed it. Voyager 1 passed through the heliopause in 2012. Voyager 2 followed in 2018. Both probes detected a sharp change in the particle environment at the crossing. Inside, solar particles dominated. Outside, galactic cosmic rays took over. That's the border between our solar system and interstellar space. Voyager 1 and Voyager 2 are the only human-made objects that have ever left the solar system. Both are still transmitting. Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos, and you'll miss what we uncover next. Crossing the heliopause, we've left the solar wind behind, but we haven't left the solar system, not even close. Far beyond the heliopause, from roughly 2000 AU to perhaps 100,000 AU, there exists a structure that has never been directly observed, but whose existence is confirmed by what we see every time a comet enters the inner solar system. This is the Oort Cloud. The Oort Cloud is a vast spherical shell of icy objects surrounding the solar system in every direction. Not a flat disk like the Kuiper Belt, but a three-dimensional globe, completely enclosing everything inside it. It contains hundreds of billions to trillions of small frozen bodies. Water ice, methane, carbon monoxide, ammonia. These are the leftover construction materials from the solar system's formation, gravitationally scattered outward by the giant planets early in their history and trapped in enormous, slow orbits that take millions of years to complete. Its outer edge sits roughly 1 light-year from the Sun, about a quarter of the distance to Proxima Centauri. The nearest star is only 4 times farther away than the edge of our solar system. The Oort Cloud has never been directly observed. Its objects are too small and too cold to detect at those distances with current instruments. What we know comes from inference. Occasionally, a gravitational nudge from a passing star or the galactic tide disturbs an object in the cloud and sends it falling inward. It takes thousands to millions of years to fall. Eventually, it arrives in the inner solar system as a long-period comet, a frozen body from the edge of the solar system, lit by the sun for the first time in its history, trailing a tail of ice turned gas. These comets arrive from every direction, not just from the flat plane where the planets orbit. That spherical distribution is the Oort Cloud signature. It tells us that the reservoir they come from completely surrounds the solar system, above, below, and sideways. An observer watching our solar system from a nearby star would see none of this. The Oort Cloud is invisible. The heliosphere is invisible. What they would see if they looked at the right moment is a bright comet diving toward our sun, a fragment of the edge briefly made visible by the star it spent billions of years slowly orbiting. From the right distance, the solar system is not a flat disk. It's a sphere of frozen ice around a bright star, and almost all of it is invisible until a piece of it falls inward and catches fire. Now we've cleared the Oort Cloud. The solar system is behind us. The sun is still visible. In fact, it's one of the brightest stars in the sky from this distance, but the planets are gone. Everything we've ever known fits inside a faint glow. What does our solar system actually look like from here? The heliosphere, that teardrop-shaped magnetic bubble, is far too faint and diffuse to see with the naked eye. The Oort Cloud is invisible. Its individual objects are too small and too sparse. What's visible is the sun itself, and from 10 light-years away, it looks like a relatively bright yellowish star. Distinctive enough to find, but not the kind of star that would make anyone stop and stare. To give it a number, the sun has an absolute magnitude of 4.83 on the astronomical brightness scale. That places it in roughly the top 10% of stars by luminosity in the Milky Way. Not the brightest, not the dimmest. A middle-aged, middle-brightness yellow dwarf of spectral class G2V. From 10 light-years away, it would be visible to the naked eye from a hypothetical planet there, but it wouldn't stand out. For comparison, Sirius, the brightest star in our night sky, has an absolute magnitude of 1.43, more than 20 times more luminous than our Sun. Vega is about 37 times more luminous. Even Alpha Centauri A, one of our nearest neighbors, is slightly brighter and slightly larger than the Sun. None of the planets are visible from this distance. Jupiter, the largest planet in the solar system, has a diameter 11 times that of Earth and a mass more than twice that of all other planets combined. From 10 light-years away, it is completely invisible, too small and too dim to detect without sophisticated equipment. What a sensitive telescope could detect is the effect Jupiter has on the Sun. a slight periodic wobble in the sun's position as the planet's gravity pulls it in a small orbit around their common center of mass. This is how we find exoplanets around other stars, not by seeing them, but by watching what they do to their star. Jupiter makes our sun wobble by about 40 feet per second, a measurable signal, but one that requires years of careful observation to extract from the noise. There are at least a dozen known star systems within 15 light years of our sun. Some have confirmed planets. Some have been studied for signs of radio emission. None have so far yielded a signal. From their perspective, looking back at us, they would see what we see when we look at them: a star, bright enough to locate, ordinary enough to overlook. From the perspective of any civilization within 10 light years of us, our solar system is an ordinary star with an invisible planetary system. There is, however, one way in which our solar system is not invisible to the rest of the galaxy, and it's something we created ourselves without intending it as a signal. Since the early 20th century, Earth has been broadcasting electromagnetic radiation into space. Radio signals, television broadcasts, radar pulses, military transmissions, all of it travels outward at the speed of light in every direction. By now, those signals have created what astronomers call the radio bubble, a sphere of artificial electromagnetic radiation roughly 200 light-years in diameter, centered on our solar system, expanding outward at the speed of light. The earliest signals from the 1920s are now about 100 light-years away. Every year, the bubble expands by 1 light-year in every direction. This bubble contains every radio and television program ever broadcast, the first radar pulses, the first satellite signals, every conversation ever transmitted by radio, all of it moving outward into the galaxy, getting weaker with distance but never disappearing entirely. From 100 light-years away, those signals are extraordinarily faint, diluted by the inverse square law across the enormous distance. An alien civilization listening for our signals would need a radio telescope far more sensitive than anything we've built. But from within about 50 to 100 light-years, the signals are in principle detectable with sufficiently advanced technology. This bubble is the only evidence of our existence that has ever reached interstellar space. The Voyager probes carry a golden record, a physical message in case they're ever found. But they'll take tens of thousands of years to reach the nearest stars. The radio signals are already there. For any civilization within 100 light-years of Earth, we've been announcing our presence for a century. Whether anyone is listening is a different question. So, what does our solar system look like from outside? From a few hundred AU, a bright star surrounded by an asymmetric magnetic bubble, shaped like a comet by its motion through the galaxy, with invisible boundaries where the sun's influence gives out and the interstellar medium takes over. From a few light-years, a middling yellow star, unremarkable in brightness, with its planets completely invisible, detectable only by the slight gravitational wobble they impose on their host star. From tens of light-years, a faint point of light indistinguishable from thousands of other stars without careful analysis. Except for one thing, a slowly expanding sphere of radio signals, moving outward at the speed of light, carrying the inadvertent announcement of a technological civilization. The solar system, from outside, is modest. The sun is not the brightest star in the neighborhood. The planets are invisible. The magnetic bubble that shields the inner solar system from the galaxy is real but undetectable by sight. The Oort Cloud is a ghost, present, enormous, and completely dark. What remains visible is a single point of light, slightly yellow, slightly warm, slightly brighter than the average star. And then there is the radio bubble, a sphere of signal expanding outward at the speed of light. The earliest transmissions from the 1920s are already 100 light-years away. The sphere contains within it a century of human communication, a record of our technological civilization growing outward in every direction simultaneously. It is the only thing about us that has actually reached the wider neighborhood. The planets can't be seen, the heliosphere can't be detected, but the radio noise can, in principle, be heard. We have no way of knowing whether anyone is listening. We have no way of knowing whether the signal, as faint as it has become with distance, stands out against the background noise of the galaxy. What we know is that it is there, spreading outward into the dark, carrying everything from early television broadcasts to radar pulses to mobile phone emissions, moving at 186,000 miles per second and never stopping. That noise is us, the only version of us that has ever left the solar system fast enough to matter. It's been traveling for 100 years, and it has a long way still to go. Now you know what the solar system looks like from the outside. But that raises a different question. In the larger map of the galaxy, where exactly is this solar system? Where are we really compared to everything else out there? Watch Where Are We Really in Space to find out.